So just wanted to thank the organizers for the opportunity to talk here. I'm very much enjoying the workshop so far and looking forward to the upcoming 3 weeks of material to come. But just as a forewarning, I'm gonna the time slot has been divided into two. I will not talk about any probability at all. I will talk about math biology, I guess, and then Thomas will talk about probability. The sort of math biology that I want to talk about that sort of inspired the probability work that comes after was done in collaboration with Fritjof Lütscher, who's in Ottawa, and Alison Shaw, who is a biologist in Minnesota and who was visiting Montreal last year. And so I gave it the biological title that had a Lee effect in it, but a lot of you will recognize it as things with bistable equations, right? But biologists talk about it as a Lee effect. I guess physicists have their own name, the Allen-Kahn equation, etc. So I will stick to the biological terminology because that's the motivation for this talk. So what I'm talking about is a theoretical ecology problem, which involves essentially evolution of different species and then their expansion in a spatial domain. And so what one is interested in is dynamics of range expansion. So you have sort of two components. One is the traits of the species, right? So and the dynamics of on the traits because of local regulation. So what you should imagine is each species has some kind of trait. This trait comes with a heritability through reproduction. And then it comes with a mechanism of mutation because traits can sort of evolve into other traits. The local regulation is the part that's sort of due to competition and or cooperation, and that affects essentially how your population numbers change over time. So how your birth and death rates are affected over time. Now, in terms of the movement in space, you have this sort of dispersal element. And so you can think of the dispersing in space, so the species moving around, as being, in many models, people think of that as independent of the trait, but there are models where you think of your dispersal ability as something that depends on your trait. And another complicating feature is that it can also affect the mortality. So there's a cost to dispersing. That's how ecologists think about it. So the dispersal can also affect your death rate. The change, so what is one interested in recording is the composition of traits in space and time. And so the composition of traits, you can, so ecologically, I think that the thing that tends to dominate some of the conversation is the aspects of spatial sorting and selection. So spatial sorting is essentially the idea that they can be sort of a stratification of which species get to which parts of space and dominate that part of space. Whereas the selection part is how that interacts with inheritability, right? So if you're at the front of the speed and then you're more likely to reproduce yourself, then you're giving an advantage to this. So if you're the lone species there, then you're giving an advantage to your own offspring type. And so that creates a kind of spatial selection for certain types because they tend to be in different regions of the space. There are other things that are interesting, such as such as what's the genetic diversity of the composition, things like gene surfing, et cetera, which I will not delve too much into. So what are the questions that we were interested in looking at is which factors affect the speed of the expansion, right? So of these various ecological facts, do some factors increase or decrease speed? And again, all of it, there's so many components that you have to figure out in which way we're going to change the parameters to see how it affects the speed. So let's start with one of the things that people have in partial differential equations have looked at, which is what if you evolve the dispersal ability? So what that means is It's something that was motivated by an experimental example on these toads in Australia, but essentially what you're thinking of is, instead of, you think that the trait and the dispersal ability are so tightly linked that you can now imagine that dispersal is your trait, right? I'm just gonna keep track of what's the length of dispersal that I'm able to do. And so I treat not just the evolution of the trait through the reproduction and local regulation, which is in this part given by the, it's really poor, sorry, my poor writing skills here, mixed partials, etc. You have the KPP term. So here, think of NT as the proportion of the type D, okay, the trait type D. Rho T would then be the overall population, right? So you have a KPP term, FKPP term that tells you your evolution bit. Then you have the usual part, which is, you know, your movement in space based on your dispersal ability, which is the first term with D as your diffusion, your dispersal coefficient. And then what they added into the equation is the ability of the dispersal coefficient to evolve by slight diffusions, plus minus, in terms of the amount of your dispersal variance is going up or down, right? And so there are various PD results obtained on this. And what was observed is generally that longer dispersals dominate, the higher D dominate the wavefront. So there's sorting, there's an increase in overall speed. And relative to what would happen if you had a single D trait of the average of the total population. And this may even accelerate over time. So regardless of, even if you introduce mortality, if it's not too, even if your dispersal tends to kill you a bit more, you know, give you a cost in terms of death, this will happen unless the mortality is too high. So what does this seem to indicate? There's sort of this general quote, well, evolution, in this case, the trait is the dispersal ability. Evolution speeds up population spread, right? The evolution of the dispersal speeds up the population spread. However, as you can see in that model, the drift term was an FKPP equation, which tells you that this relies on having the highest growth rate at low population levels, right? So the guys at the front, they don't have competition, and they can they have their growth has the highest derivative there, and so only really the competition is what, you know, when you reach a certain amount of individuals at a location, that's what keeps you back, right? And now you think, okay, what if I introduce another thing, which in ecology is called the Allee effect, where having low population levels can be detrimental, right? So you can imagine different reasons why this can be the case. The easiest one to imagine is mate finding, right? Low population numbers, you can't find mates around, you're not going to reproduce. So what essentially you can think of that is that at low population levels, you need cooperation to survive, right? So you need there's some kind of, at overly low levels, you don't have enough cooperation, so you need to get to higher levels to have some cooperation. So there are various results that were derived for that, and mostly from the sort of genetic point of view, that there's higher genetic diversity in these when you introduce the Allee effects, you have interesting things like genetic diversity going up, gene surfing is being allowed. And the idea from let's look at the speed and what can happen in this case, which are PDs that, to my knowledge, have not been explored yet. So the previous, what's called the Kane-Todes equation, has been done only with the FKPP term. Is here you would think that there's disadvantages to the long dispersal, right? Because your density can go below the threshold if you're too far out. And so that can hold you back. And so there are some results that will tell you that if the Allee threshold, which is the part at which in your, did I give the bistable equation? No, yeah, sorry. So if the amount that you need in order to find your mates is too high, then somebody with a lower dispersal rate can invade and actually take over the population, and that will slow down the weight. So there were some results that were obtained for that by simulations or by this linearization technique that Korolev did. And essentially they implied that there's a trade-off between Allee threshold and the dispersal length. So you can't have it both ways. So what we're going to do here is I'm going to talk about a population model with a trait that's equal to the dispersal. And so the model is, this is going to be an integral difference equation model, so a deterministic model in discrete time. So you're going to have basically two phases, the reproduction phase, the dispersal phase. In the reproduction phase, you have this pair formation, and that's what's going to create the Allee effect. Because so you have it density dependent, but trait independent. So a certain type with a certain dispersal distance can mate with any other dispersal distance. So the cooperation can come into play there. But if the density is too low, then the pair formation is disadvantaging you. And so you will have fewer offspring. Then the next thing is you have a trait inheritance, right? So what happens in that sequence will decide what proportion of traits you have in the next time period. Then you can introduce mutation that individuals can trade up traits or trade down traits, followed by death of parents, offspring survival. And so the offspring survival is where you can put in a capacity and get the usual sort of competition regulation into your equation. And then you have a dispersal phase where all of the individuals they have been reproduced, just disperse in various parts of space, given using a kernel that has a certain value for the parameter that you think of as dispersal variance. So the local regulation parameters are the average number of offspring, the maximal survival capacity. The other parameters are dispersal variance and the mutation rate. So essentially you go through the motions of saying, okay, at time t, if I have a certain density of, so this, for now, just to follow it, this is one trait, right? So D is fixed here. Essentially you go through the process of having this kind of bistable equation for how many pairs or how many offspring you're going to create in the next round. Then you're going to, including the cutoff, if you are exceeding the capacity n, then you only get to keep n of the individuals, right? So you have an average B times the number of pairs you formed, and then you cut that off with the n. And so what you're getting is a difference between, the increment in terms of population size is exactly this equation that's bistable that you saw in the talk earlier today. You have the dispersal phase where you just use like a Gaussian kernel with variance D to disperse the individuals in space. And because this is an integral difference equation, you do not clearly see what you would in the bistable equation you see as an Allee cutoff. I mean, sort of the location cutoff, you actually have to solve an integral and see when do you have a positive speed, but these are known to have a constant speed wave propagation under this constraint. Otherwise, they have the wave retracts back. Now, this is unfortunately very sensitive to initial conditions. So both the height and the support of the initial conditions are very important in this case. So this is something to keep in mind, right? So when we did our work, we made sure that the initial conditions were very carefully chosen to make it equal for the different traits. So the multiple dispersal type would do all of the same, except you would keep track of the dispersal value for each individual, and then you would let their dispersal kernel use that as the variance in terms of the lengths. So what we wanted to compare is the speed. Suppose you just have no mutation. So the types are, you start with some some initial conditions on how many different types you have of, of how many different individuals of the different types you have, and you evolve that in time. And then you compare that with the same scenario, but you allow mutation. So you allow changes between the traits for the fixed number of traits that you have. So you're not allowed to increase beyond what you already have at the start, just the traits that you already have. And you're wondering whether that would change, whether that wave would propagate more, faster or slower, right? And so the kind of maybe intuitively clear things that happen is that if you have a mutation, that means at any point, you know, anybody can change to one of the other traits. All the traits will have the same speed. So you see these waves of all the different trait types propagating at the same speed. So they essentially form a single traveling wave. Whereas if you turn off this mutation, and so you just have whatever you have at the beginning and you see what will happen over time, then only one trait survives and essentially will determine the speed of the wave, right? And so the question is, which of the traits, so if you start with two traits, is the longer or the shorter dispersal going to win over? And that depends very much on how your Allee threshold or sort of how those dispersal values compare with the Allee threshold. So here, if you are in the highly competitive phase, then the longer dispersal, the guy who can disperse further, will dominate the front. If you are in the more cooperating phase, then the shorter dispersal is going to basically take over the wavefront in the longer dispersal, create the traveling wave. Okay, and so this is a schematic of, you know, depending on because we have two parameters, the capacity and the branch number. This is a schematic of in which cases which one of them wins, and you can see that it's a sort of a nonlinear profile. These are the graphs of what happens with two dispersal types. So the bottom is, as I said, when you have mutation, the bottom is both of them keep going. So the top panel, sorry, these panels are shorter, these are the longer. So both of them are going to continue, but just one of them is going to be a little more prevalent at the front of the wave, right? But both of them continue on. When you turn off the mutation, you just basically there's a winner takes all kind of situation where, depending on whether in the more cooperative stage or in the more competitive stage, in the cooperative stage, the shorter one, which is on top, takes everything, and the longer one just sort of dies, it like doesn't make it anymore, and the opposite in the other case. And this is what happened. So of course, with the two dispersal traits, this is kind of easier to see what's going to happen. When you have multiple dispersal traits, by fine-tuning where the cutoff is relative to these traits, you can basically have any one of the particular ones be the one at the wavefront. So again, when you have mutation, they're all making it on the wave. That's the bottom panel. They're all going to make the propagating wave. On the top panel, essentially here, the parameters were tuned so that the green, which is not the highest one, right? Like it's somewhere in the middle, the green was the one that dominated everything. So he wasn't the winner at the beginning, but eventually he won over. So everything depends on how you choose the parameters. You can pretty much isolate any one of the different dispersals to be the winners in the long run. Okay, so again, nothing probabilistic here. Now on to the mathematical questions that I'm happy if anyone wants to have some input on this. So sensitivity to initial conditions, can stochastic effects early on play a role? I don't know. Obviously, this would be interesting to do in higher dimensions with the sort of locally regulated or reproduction rule, whether it's stepping stone model or some measure value process. And of course, you would want to derive scaling limits from the individual stochastic models into either deterministic or sort of either law of large numbers or CLT type results. I think I should give Thomas my time here. But yeah, essentially, you can imagine how you could start from a birth and death process that will have these features. We'll keep track of everything. And then essentially what you would want to do is derive, you can easily derive the deterministic limit, right, of this, where you would get some nonlinear integro-differential equation, where the dispersal types are coupled through the birth and rates and the mutation. But you should also be able to get a stochastic limit. And, you know, in the spirit of the measure value process that, you know, for a single dispersal type and KPP type equations we've seen before. But here's where Thomas will say something about dimension one and purely local competition. So at the exact spatial location, so not looking to compete with the neighbors. Right. Okay, thank you for your time and enjoy the rest of the.
I think we'll leave questions until the end.
There might be questions, right?
Well, should we sort of have
I don't
joint?
know.
It's maybe we can.
Or people can ask me tomorrow. I'm open to that. I just want to let him do his part.
Yeah. So I was going to suggest we have like joint questions at the end of when Thomas is finished, if that's okay with both of you.
Okay. Thank you, Lea. Thank you, everyone, for being here. I'll just get right to it. So she's talked a lot about things you can talk about when you have different types with different dispersals. And that's something that we'd very much like to do. But for the time being, we'll now get into a single type scenario. So does that work? Okay, so I want to talk about the equations I'm going to draw look a lot like some of the equations we've seen, but I'm thinking of them from this ecological setting rather than the population genetics setting. So I'll talk a bit about where they come from. And to review straight off the bat, just something quite classical is that when we want to take a scaling limit of a branching process that's not in space, you know, if you take the proper scaling regime, you get what's called Feller's branching diffusion. So if you have finite second moments on a Galton-Watson branching process and say it's critical, then you're going to get under scaling limit the solution to this SDE with theta equals 0. And if you then make you have supercritical processes and you scale in such a way that you want to get a stochastic and not a deterministic limit, then you'll get this equation here, Feller's branching diffusion, where we've got this upward drift. And this is a continuous state branching process. It's extremely well understood, and much like a discrete supercritical branching process, it will survive for all time with positive probability. Now, if you want to model a population that actually exists in some capacity, then probably it's not just going to grow exponentially without bound forever. There's going to be some kind of limitations. So you can model this as having, you know, there's limited resources for which the individuals are competing. If you then, okay, you can just take the stochastic model and add in this term, which I'm adding by this quadratic term, and we get what's called the logistic Feller diffusion. And I think there are limit theorems where if you actually start with, you know, discrete type processes with this kind of dynamics, you can obtain this as the scaling limit, but don't quote me. So this second process, okay, what we see when the states around theta is some positive parameter that's acting as a carrying capacity, because when the state is there, then it's basically critical. And when it's above that, it gets driven down. When it's below that, it gets driven up. So it likes to stay there. But ultimately, some big fluctuation is going to kill us, and we're going to go extinct almost surely. So what I next want to do is look at a population like this, but embedded in space. The motion is going to be Brownian, be the SPDE version of that SDE. So we have, again, the square root coefficient is giving us branching type behavior. This isn't Wright-Fisher. Our solutions can go above 1. And U of Tx is then going to be the local population density at a point in space-time. And otherwise, it's the same dynamic. So it looks like the FKPP equation. I've got this theta multiplying the U term. And again, that's going to be acting as a sort of carrying capacity. And the question is, if I start this equation with some integrable initial data, so I have some finite mass in my population, is it possible that it survives for all time? And obviously, we've just seen that if we don't have anywhere to go, if we don't have any space, we go extinct almost surely. So it stands to reason that if this does survive, you know, indefinitely, then it will do so by means of kind of propagation and colonizing new areas. If it stays put, it's going to die. And of course, I didn't say, but W is space-time white Gaussian noise. And so the theorem, this is quite old, it goes back to a work of Mueller and Tribe. They prove that there's a phase transition for this SPDE. They viewed it as arising as a scaling limit from a voter model, but clearly it serves my purposes here as well. And so for theta sufficiently large, if we have a large enough carrying capacity, the solutions will survive indefinitely with positive probability. And if it's too small, then they will go extinct in finite time, almost surely. And a quick note on, I'm not going to ever talk about the initial data, whether here or for the bistable ones. And that's because when we've got this Wright-Fisher type noise, there's some nice tricks available to us that basically, if we don't have any of the reaction term, it's a super Brownian motion, and we can actually represent up to finite times this as like a measured change. So there's a Girsanov theorem for measure valued processes, wherewith we can express this as a measured change super Brownian motion. And then we use a little absolute continuity tricks for super processes. And it turns out that for one integrable initial data, you know, if the survival probability equals 0 for one integrable initial data, it must for all. So all kind of finite initial data ends up being the same. So that's FKPP. Lea's been talking about bistable stuff, and so I want to move there. So the Allee effect, again, is going to be something where we have a positive correlation in the reproductive fitness with the local population density. And so we're going to view that as being, well, I'll just show you the equation I use. So I say Allee effect, or I say bistable equation. In either case, this is what I'm going to be talking about for the rest of the time. So we're still going to have competition, and now we're also going to have that unless, you know, if the density is below a certain threshold, then it also we have subcritical behavior, and it's just between this upper and lower threshold when we have supercritical behavior. You know, if I just took an ODE version of this, it looks something, this is, you know, kind of where my face plane looks like. This is where I'm good, and otherwise if I'm down here, it's trying to kill me, and otherwise if I'm up here, it's trying to bring me back down to the upper threshold. K2 is now a carrying capacity, and K1 is some threshold associated to the Allee effect. Now, do I have anything else to say about this? I don't think so. Now, I'm about to scale this all away, and, oh, wrong button. Here we go. So by scaling, I'm going to write it as this instead. So now it's scaled so that the carrying capacity is 1, and the lower Allee threshold is gamma, which is between 0 and 1. So now it's just this, and I've got an extra parameter theta I can play with. Now I'm going to generally view gamma as fixed. And the reason is this, in an analogy with the Mueller and Tribe result, I'm looking for phase transitions in the parameters of this system. But the deterministic system, you know, if I forget about the noise, erase the blue part, then I have some kind of reaction-diffusion equation with a cubic nonlinearity of the Allen-Kahn equation. If you vary gamma for the Allen-Kahn equation, that's going to dramatically change the behavior. So if I'm allowing in my stochastic regime to change parameters in such a way that I'm changing gamma, in particular varying it over a half, then I can't really be sure my phase transition is going to be stemming from stochastic effects, because we already know that the deterministic effects are dramatically different in those regimes. In particular, you know, if gamma is on one side of 0, then basically the one state is energetically favored, and so the traveling waves to this equation have positive velocity. And, you know, symmetrically, if it's on the other side of 1/2, then the 0 state is energetically preferred, and we have traveling waves with negative velocity. When I mean energetically preferred, I'm just saying, you know, I'm not going to draw it. Yeah, right, that's it. So the point is that our potential here is like the negative gradient. The reaction term is like the negative gradient of this double well potential. And so just depending where you put gamma, one of these is deeper, and that's going to tell you which way the wave is moving. So now I'll tell you what we can prove. I'll tell you how we prove it. I'll tell you what we want to prove and why we can't prove it. And then I'll share a few other thoughts I have. And I'm going to forget the case gamma equals 1/2, which in that regime, of course, the traveling wave doesn't travel, just kind of stays put around the origin by symmetry. So what we can prove, you know, analogously to the Mueller and Tribe, but not quite as nice as you'll see because it's not sharp, is that yes, for sufficiently small gamma theta in that equation, we'll have almost sure extinction, and for sufficiently large theta, we will have survival with positive probability. Now, I wrote there's two critical parameters, theta c prime. One, of course, expects them to be equal, but what we can prove comes nowhere close to showing that, and really that's the crux of it, is that this equation does not allow the same techniques that allow you to get the sharp phase transition for FKPP. So I'll talk about this in just one moment. There's a phase transition for the extinction and persistence for this equation with finite initial data. But again, sharpness isn't proved. And this is, of course, in the case when we have positive wave speed. Quick note on negative wave speed. I always took it for granted that you would have almost sure extinction regardless of the value of theta. Because think you've got the bistable equation in this case is favoring the unoccupied state 0. So if you take a traveling wave, the 0 state is actually going to invade the 1 state, which means that these things should be converging to zero, especially if you're starting with some finite initial data. Moreover, we've got Fowler noise. Now, Wright-Fisher noise treats the states 1 and 0 equally. It doesn't make any preference. Fowler noise does not do the same thing. You can look at it, it's a square root, right? And multiplying a Gaussian, it's a martingale. But the point is that 0 is absorbing to it because the square root coefficient vanishes at 0. So it never kicks you out of the 0 state. But if you're in the 1 state or nearby, it has, it's a positive number. So there will be fluctuations and it can kick you out and kill you. So in this case, when gamma is between 0.5 and 1, both the deterministic dynamics want us to die and the Fowler noise wants us to die. And I'd really taken for granted until quite recently that this should not be that challenging a thing to prove. But then I gave it a bit of thought and I realized I only knew how to prove this for small values of theta. So if someone knows the proof for this, I would be grateful if you could tell me, or I would also just like to talk about it. And if it's possible that it has an easy proof. So if the proof's a bit easy, then be discreet when you tell me. But that's all I have to say now about the gamma between 0.5 and 1 case. And now we'll go back to talking a bit about how you prove these transitions between extinction and persistence when the deterministic dynamics, favor the occupied state and the traveling waves have positive velocity. I won't get too much into the proof techniques, but I'll sketch basically how Mueller and Tribe and what we're also doing for our proof to prove extinction and persistence. So in the extinction proof, you can rescale the equation if you like, so that your free parameter is sitting in front of your Laplacian, and you can look at so small theta corresponds to small diffusion. And this is a handy way of looking at it, because if you have really small diffusion, then you can think of your population as being, almost stuck where it is in space, and then use the analogy back to, the logistic branching process stuck in space, or now, a process with a cubic reaction term, but no spatial component, which we know of a large fluctuation in the noise will almost kill. So what you do is you view your populations consisting of different subpopulations, and you call each of these a brick, and then the bricks will either split or die, and then you make a branching process out of them. So how this works is, you have some sub density of your total population, and in some amount of time, it's either going to go extinct from fluctuation in the noise, or it's going to spread out far in space, or it's going to grow. But for small values of theta, the overwhelmingly likely option is that just goes away. And so if it does spread out in space and it does grow, then you just subdivide what you get from that into a bunch of smaller bricks, and that's how you get this branching process. So it's either going to split by propagation or go extinct by staying put. And you can compare this to a subcritical branching process and show that it goes extinct. This is what Mueller and Tribe did. I think before I said they were 1994. It's one of those years. And Alison Etheridge also used this in a paper where she studied similar, but also sort of different model called the Bulker-Pakula model, which she realized via a super process. And this comparison with a subcritical branching process was present there as well. To show survival, it's used, what we're using, what Mueller and Tribe use, and what's used in a number of places when you can, is this comparison with an oriented percolation process. Likewise, you kind of think of the density is being subdivided into different spatial regions, and then you kind of discretize time, and you say, okay, from one time step to the next, I've got this little chunk here, and so I need to obtain bounds on the probability that this chunk here, fertilizes a chunk of equal size in one of these adjoining sites in the next time step. And this makes heavy use of the comparison principle, as we'll see. But if you can obtain sufficient bounds on the probability that a brick in this spot causes a brick in an adjacent spot in the next time step to be occupied, then you can iterate this through time, and you get this, it's oriented percolation because you have the arrow of time pointing up. And if your comparison is with an oriented percolation of sufficiently high parameter, then this is a supercritical oriented percolation, which will have infinite clusters with positive probability. You get your survival theorem. The last thing is that this is what I've already mentioned, the sharpness of the phase transition, and how it works for the FKPP equation is that they can prove extinction for really small, they can prove survival for really big theta. And then they've got this monotonicity, which is basically you can take solutions to the equation with different values of theta and construct monotone couplings for them. And for the point is that you cannot do this for the bistable equation. So quickly to discuss monotonicity. Now I think I've written this wrong. The first one should be theta u minus u squared. But the point is that that equation omits monotone couplings, and that you take the same initial data and you can construct coupled solutions with to the equation with two different values of theta such that they will remain ordered. And this immediately implies that the survival probability is monotone in theta, which immediately implies that the phase transition is sharp. Now, equation 2, the Allen-Kahn equation that we'd like to consider with the Allee effect does not emit monotone couplings. You can imagine if you have your state is such that it's sitting below gamma, where it's being driven down, then if you crank up, because you want to think of increasing gamma as helping you, but anywhere where the state is actually below the Allee threshold, the more you crank up gamma, the worse off you are. Theta. Was I saying gamma? I meant theta. That's okay. Everything I just said, null and void, swap theta for gamma. Thank you. So the non-existence, the fact that you can't construct these monotone couplings then means that barring a novel technique, basically, we can't get sharpness for this phase transition. Something I quickly want to mention is that this is kind of extending to other models. A kind of monotonicity that both of these equations have is just the parabolic comparison principle. Solutions which are ordered at time 0 remain ordered. And you take this for granted, you're dealing with SPD and what have you, but there are a number of interesting models, especially with non-local competition. So where you have some kind of kernel and a convolution. And this is often what's called a Volcker-Pacula model, because you have competition with individuals not at your exact location. And in this case, you actually lose, this ordering as well, this comparison principle. And so there's some nice work by, Pascal and Sarah on such a model, as well as I think some other people in the room have worked on this kind of thing. And in this case, you don't really, I suppose I put this up to say there's a lot of interesting work when you don't have that. And also, even lacking monotone couplings, it's very nice to still have the parabolic comparison principle at the end of the day, because that is one of the things that makes the oriented percolation proof tick. And when you lose that, you have to work a lot harder. And hopefully I have about a minute left, and this is just, I'm going to bang my drum about the differences between Feller and Wright-Fisher noises, and try to relate some of this to a lot of the discussion on traveling waves. So the heuristic, and I don't think this is really proved anywhere, but I think if you think about these equations very much, you've probably thought this kind of thing, which is that for the survival probability to be positive when you have finite initial data, should basically correspond to when that stochastic equation with front-like initial data has traveling waves with positive velocity. Because there's no better indication of the tendency of the occupied state to invade the unoccupied state than that there's a traveling wave that moves in the right direction. Now, this stops short of being a proof for a number of reasons, including, if you can study invariant measures for these equations and which initial data will converge to invariant measures, then I think, proofs of this via this kind of idea become a possibility. But as far as I know, at the time being, it's largely kind of an heuristic I use. And then I'd like to relate that finally to what's known, because some of the results in the literature are more tailored towards Wright-Fisher noise, which, as I said, is symmetric between the two states 0 and 1, as opposed to the Feller noise that I use here. So first, you can, theta has so far been the coefficient on the reaction term, but you can scale that, and it's going to be epsilon is equal to epsilon of theta, and now you're just looking at the equation with a variable noise coefficient. You have a high noise regime and a low noise regime. And my base impression is that the low noise regime, Feller noise and Wright-Fisher noise should be the same. And there's evidence for this. The paper about the wave speed correction, Mueller, Mitnick, and Quastel, I think, is actually stated for both Feller and Wright-Fisher noises. And so that, in particular, the traveling waves have the same correction and so on. But when you take when we want to look at these phase transitions, so it's not just for asymptotically small noise intensity. In particular, we're interested in the equation for large noise, and that's where you should probably expect dramatic differences between Wright-Fisher and Feller noise. And again, that's coming from the fact that the Feller noise is going to adversely affect the 1 state, but not the 0 state. So there is some work. I think Lea has a paper with Carl Mueller and Leighton Mitnick on reaction diffusion equations in the large noise regime, with Wright-Fisher noise studying the asymptotic wave speed velocity as the noise intensity goes to infinity rather than 0. So that's very interesting work. But I don't think that helps us infer anything about the large noise behavior for the Feller case, because when you, for example, if you go back to the theorem of Mueller and Tribe, and you take the noise intensity to be such that you don't expect solutions to, that the solutions go extinct with almost surely, then one also expects that you don't have any traveling waves to this. So what's known for the Wright-Fisher noise is that there are traveling waves, their sign may change, but and the asymptotics of the velocity are known as epsilon goes to infinity. Whereas in the case of Feller noise, I think when you go beyond this threshold for extinction, little to nothing is known about the existence of traveling waves, and there does not seem to be a clear roadmap about how to infer behavior from that because of this. I think I lost myself a bit in the last moment there, but it makes it a good place to stop, and I thank you for your time.
So thanks very much to Thomas and Lea. Any questions for either, both of them?
So do we have any guesses as to whether the transition is sharp?
I think it's sharp.
Okay. I've worked on such a type of model and I thought mine was sharp too.
Pardon me?
I said I've worked on a similar model where monotonicity breaks, and I also thought mine was sharp, and I also still don't know whether it is. So
we should talk.
Yeah, sure.
We can make a support group, or we can prove a theorem.
Right, one or the other. Yeah.
More questions? Or are there any questions online? I had a silly question, which was like, can you take gamma to be negative? Like, can you do your proof through if you take gamma to be negative? Things that
So if gamma is negative,
then you lose. So you lose the other root basically, but so it's not bistable anymore. But
I've not thought about it. Presumably, because I mean, you're getting closer to FKPP as that happens.
Yeah,
is that right?
yeah.
I should check before I say yes. Is what I'm saying, but it's plausible.
Any other questions? Well, let's thank both of the speakers again.